Hello, I'm Mohamed Furkan Yabasa, and I'm recording this video to present my project for the course Quantum Computation. And the project is about implementation of Shor's algorithm in Qiskit in Python. First of all, I will try to explain the algorithm, and we will go over the algorithm once. And then we will see the code that I wrote for the project. At the end, we will have a demo session. We will see the code in action. We will run some examples, and we will examine them. Let's start with the algorithm explanation. Shor's algorithm is used to find the prime factors of a number n, which is multiplication of two primes. Algorithm starts with picking a number a, which is less than n, and we see if a and n are relatively prime, which means greatest common divisor of a and n is greater than 1. If this is the case, we are lucky because we already found one of the factors of n, and we simply divide n by this factor and we get the other factor, and we terminate the algorithm here. But if this is not the case, and GCD of a and n is 1, we proceed to step 2. In step 2, we compute the period of the function a to power x mod n, and we call this r, and we examine r here. If r is odd, we go to step 1 and pick another a and proceed. If r is even and this condition holds, again we go to step 1 and pick another number a. But otherwise, we go to step 3. And in step 3, we have a straightforward computation. We know that a to power r minus 1 is a multiple of n, and we know that r is even. So we can open this term as a to power r over 2 minus 1 and a to power r over 2 plus 1. And we can write n as p multiplied by q. So p must divide one of these terms, and q should divide the other term. We simply calculate GCD of this term and n, and we compute the GCD of second term, this term, and n. With this way, we get p and q of the prime factors of n. As you can see, Shor's algorithm is a straightforward algorithm, at least for the classical part. But the challenge is in here, find the period of the function. This part can be solved in exponential time in classical computers, but for quantum computers, it is solvable in polynomial time. So let's see the code. You can access the code in this path. I put the code here for your access. The program takes a number, the factor, and it gives it to the function myShor. And myShor takes this number and returns the factors of it, the prime factors of it. So I will not go through all the classical steps here in the algorithm. As we said, these are straightforward calculations. But for the period finding, we are using the quantum circuit. Period finding function finds the period of the function a to power x mod n, and for that it builds a quantum circuit, which looks like this one. The circuit takes two input registers, the down register and the binary representation of n, and it's initialized with 1. And the upper register, we generally use 2n qubits. I use 2n qubits as well. And first of all, we apply Hadamard transfer to the first register. Actually, we can apply also quantum Fourier transfer block here for the first register. They both give the same result. They both give the superposition of all the states with the same amplitude. And after that, we applying the block of the modular exponentiation block here, our function. And at the end, we are applying the inverse reactivity to the first register, and we measure it. With this measurement, we get the period of the function here. And Let's see the code again. Here in the quantum circuit, we first applied the upper register QFT. We didn't apply Hadamard. We can apply Hadamard as well here. After that, we put a NOT gate to down register the least significant bit to get one value. After that, we applied the modular exponentiation block. I took this block. I mentioned in the references. You can see it. These functions here calculates the modular exponentiation. This is kind of hard to implement in a circuit because it's the general format list. You can see in the paper here, in this paper, it's similar to this paper implementation in our code as well. You should use some add gates, inverse add gates, some QFT and inverse QFTs, and some multiplication blocks and some swap blocks. I mean, it's a kind of complicated implementation for general case. So after implementing the modular exponentiation block, we apply inverse QFT to the upper register and we measure it simply. And we run the circuit 1,000 times and we got our result here. And I processed the result a little bit because for the cases that R doesn't divide M perfectly, we got some low probability result as well. Actually, let me show you. I run the program for 21 here, for example, because 21 gets some like a bit long. I run it for 21, and it selected A as 2 in step 1, and in step 2 is execute the quantum circuit, and we get this result. As you can see, the results, we see some results like seen in one time, in 1,000 times. It's in one time, 3 times, 5 times. These are not wrong results, but they are near to the results we want. For example, this result we want 0. It's normal. It's 120 times we see it. It's 853. And we see some results around these one results. So I just put a processing this here. I put a threshold. I calculate this standard deviation of these numbers, and I put a threshold. And I didn't take like just this one to one example, and I get just the numbers I want here. And as you can see, our period calculated as R is 6 and factors 7 and 3 for 21. And how I get the period 6 here, I just simply get the list value here other than 0, which is this, and this is actually k times m over r. M is to the power 2m here, the upper register maximum value. And simply, if you see this graph, so for example here there's 8 qubits in the upper register, so maximum value is 512 here, and it gets some periods here, and these are actually one time m over r. R is here for it should be 6, I guess, and m over r, m is 512 over r times 1 times 2 times 3 times 4. It goes like this actually. So the results I get here in terminal here is this results, and I get the list value, which is k equals 1. So this is exactly m over r, not exactly because r doesn't divide m perfectly here in this case. So it's very near to that. So I just take this value and I divide m by this value and I round it to integer, which is 6. So I use such a logic. And let's run this program for 15, for example. Let's see what will happen. we got lucky. We found A as, we choose A as 5, and it's already a factor of 15. So A is 7, is selected A as 7. So it's running the quantum circuit here. As it gave R as 4, it found R, which is correctly, and factors found as 3 and 5, which is correct. Let's run one more time, 15. It's calculated again. It will give the same results. Don't eliminate any because M perfectly, so we don't have like low probability results. Let's run one more time. Let's see what will it give. Selected A as 14 and it's executing the quantum circuit right now. Let's see what will happen now. It gives R2, but doesn't hold the this condition holds. So we don't want this. So it goes to step 1 again, and we got lucky this time. It found luckily 3 and 5. So the program runs in a way, and the algorithm is. I try to explain the algorithm. I think this is all I want to say, and you can see the references here. You can access them and see them. And this is all I want to say. Thank you for listening. Have a nice day.